So get ready for some more geometry today. Today we are going to be talking about what's called a polygon or polygons. It says what will you learn today? You will learn how to find the interior angle sum of polygons. Now I mentioned the words interior angle sum in your last lesson when I was talking about the interior angle sum of a triangle being 180 degrees, but now we're going to talk about the interior angle sum of different polygons, so not just triangles. All right, let's get started. So in order to talk about polygons, we first need to know what they are. So a polygon, it says, is a closed plane figure made up of three or more line segments that intersect at their endpoints. So these are some examples of polygons. It says it has to be three or more line segments that intersect at their endpoints. So here's some examples that will help you understand that a little bit better. Here's some examples of things that are not polygons. Not polygons. So I'll just draw some of those up here. So some examples of things that are not polygons. Well, just going based on the definition, it says a closed plane figure. So if you have a figure that is not closed, so something like this, where I've got an endpoint here and an endpoint there, it's not closed, I've got this gap here, that is not a polygon. If I've got, it says a closed plane figure made up of three or more line segments. So they have to be line segments. If I've got a shape with a curve in it, that is no longer a polygon. Three or more line segments, if I try to make a polygon out of two line segments, oh, that's not going to work because now it's going to be open. So I need three or more, and that's why this triangle is considered the fewest number of sides to form a polygon. And then it says they have to intersect at their endpoints. So if I have one that goes beyond the endpoint, so something like this, my endpoint's up here, that is not a polygon. The line segments have to intersect at their endpoints. So these are all not polygons. Another example would be a circle because that's obviously not three or more line segments. All right, so we have two types of polygons. Convex is the first one, and then concave will be the other one. So a convex polygon, it says when all line segments connecting any two vertices lie entirely inside of the polygon. Vertices are just where the two line segments meet. So in a polygon, it will always be where the two end segments meet each other. So I'll just put a little note on here. The vertices are where where the two line segments meet. Where the two line segments meet. So it says again where when all line segments connecting any of those vertices, so any of these points where the two line segments intersect, all of these are vertices. If you draw line segments connecting those vertices, you start at one vertex, you go to any of the other from that vertex, or start over here, you go to any of the other ones. All the line segments connecting any of the vertices lie entirely inside of the polygon. None of them are outside of the polygon. And you always get these cool star shapes when you do this. This is not convex. So the reason this is not convex is because if we look at our a couple of vertices here and we try to connect them, this line segment is outside of the polygon, and this says that all line segments must be inside of the polygon. So this is not convex. This is actually what's called concave. And I love the definition of a concave polygon. It says a polygon that is not convex. So you have to know what a convex polygon is in order to know what a concave polygon is. Based on this definition alone, a polygon that is not convex. In other words, a polygon where all these line segments connected to the vertices do not lie inside of the polygon. At least one of them lies outside of the polygon. My easy way of remembering concave polygons is from this word right here, concave. So it's a polygon with a cave in it. If you have any kind of divot in your polygon, I'll just draw an example to really emphasize my point here. If you have any kind of polygon with any sort of divot in it, like the star here, you will always have a line segment connecting at least two of those vertices that lies outside of the polygon. So here I've got two vertices there. If I try to connect them, I am outside of my polygon. And again, as I said, my easy way of remembering it is I just think of, give me a second here, I got to do a little drawing. Feel free to fast forward if you don't want to watch me draw, but I'm going to have a little fun here. All right, so I'm going to go ahead and make a little fire. That's a good fire. Put a little orange in there. Yeah, that's good. Oh, I don't know, a little more red on the bottom there. Good. We'll make it a little smoky fire. That's good. Okay. All right. Why not throw a little dude in there? Here he is, hanging out in his little cave. And let's make him roast the marshmallow. Beautiful. All right. So concave means that it's a polygon that has a cave in it. So this right here, this is your little cave. All right. So if you can make a cave, if you've got a cave, it's concave. But the formal definition says a polygon that is not convex. All right. So on this one, another vocab term, like I warned you in the first section of chapter 5, it's a lot of vocab. Geometry has a lot of vocab in it. We have another vocab term here called a regular polygon. A polygon where all the sides and angles are congruent. So everything in here is congruent. Every single angle measure is the same measure. Every single side length is the same length. And I wrote again over here, symbols are used to show congruence. The curved symbol here for the angle marking is showing that these are all the same measure. And the tick marks on the side lengths, those are indicating that those are all the same length. So that's a regular polygon, and that term's going to pop up in this section a little bit. One more slide with some vocab on it. We've got classifications of polygons. So it says polygons are classified by the number of sides of which they are made. The name of a polygon has a prefix that coincides with the number of sides. So a triangle is called a triangle because there are 3 sides. Just like a tricycle has 3 wheels, a triangle has 3 sides and 3 angles. A quadrilateral, quad implies 4, pentagon implies 5, hexagon implies 6, heptagon, or also known as a septagon, implies 7, octagon, so oct implies 8, nonagon, non is 9, and decagon is 10. And in pre-algebra, we are not going to go past 10 sides, so triangle, quadrilateral, pentagon, hexagon, hepta or septagon, octagon, nonagon, and decagon. Those are the only ones that I'm going to be testing you on. And actually, I'm sorry, we're doing online school. So you might see one of those pop up in one of your weekly quizzes, which count for homework points. So I'm not going to be testing you, I'll just be quizzing you. But those are the ones you're going to potentially see. After you get past a 10-sided polygon, there are names. The one that comes to mind, a 12-sided polygon is a dodecagon. So there are names for them, but I'm not going to go past 10. After we get to 10, let's say for a 25-sided polygon, we'll call it a 25gon. 25gon. So we're not going to keep naming them after we get to 10 in pre-algebra. All right, let's move on to our one example for this section, and only one. It says find the sum. Find the sum. That means we are going to add. Find the sum of the interior angles of the polygon. So this is what you're going to be seeing on the first assignment that I'm actually going to be walking through on a video so that you can see how we derive the equation that we're going to have to use in the second part. So typically I would have given this to you in class and had you struggle through the assignment a little bit, and then you could build the equation, but I'm going to help you through it. So this example though says find the sum of the interior angles. So here's how we're going to do that. We're going to pick any of the 2 vertices. So I'm just going to first indicate all my vertices here. Here's a vertex, here's another vertex, and then just go all the way around. These are all different vertices of the polygon. Sorry if you can hear my daughter screaming in the background. My wife put her down for 2 seconds and she started screaming. But this is the one example, so I just want to get through this one real quick. All right, so indicate all the vertices on here. Now, if I take the vertex and connect it to all the other vertices, well, this one's already connected to that one. So I'm going to draw a line segment going over to the other one here, another line segment going over to the other one there, line segment going down here, and then this one's already connected by that line segment there. So you take a single vertex and you connect it to all the other ones. You don't keep going to all the vertices and connecting them. We're not drawing that star shape that you saw in one of the previous slides. If you do that, what you end up forming is triangles. This is a triangle here. Here's another triangle there, a triangle here, and a triangle there. So we actually have a bunch of different triangles. So again, I've got a triangle here. I've got another triangle right here. One more here. And one last one right here. So I just ended up building 4 triangles. 1, 2, 3, 4 triangles. Now, the helpful thing with building triangles in a polygon is that we know the interior angle sum of a triangle. So if you know the interior angle sum of a triangle, you can find the interior angle sum of any polygon. So in this red triangle, if I take these angles, if I take these angles and I add them up, I know I'm going to get 180 degrees. So this angle plus that angle gives me 180 degrees in that first triangle. If I look at the second triangle, this angle here, this angle there, and that angle there, I know that if I add up this angle, and that angle, they are gonna also equal 180 degrees. Their sum will equal 180 degrees. So if I keep going around this triangle, adding up these angles, I know that I'm going to get 180 degrees there. And adding up these three angles here, I end up again with another 180 degrees. So if you look at the overall shape, this overall shape of this polygon, all of these angles together form the angle of the polygon. This angle is an angle of the polygon. These two angles together give me the angle of the polygon. These two angles together give me that angle of the polygon. These two are this angle here, and then I've got this angle as part of this black triangle as well. So I ultimately end up with all of the angles in this polygon. By the way, it's 1, 2, 3, 4, 5, 6-sided, so it's a hexagon. So I end up with all the angles in this hexagon by breaking them down into smaller pieces, which make up my triangles. So if I want the sum of the interior angles of the whole polygon, I just need to figure out how many 180s can I make, how many triangles can I make, and then how many 180s do I have here. So I can make 4 triangles, so I've got 4 180s. So 4 times 180 degrees, that's the sum of the interior angles of the entire polygon. So that's 720 degrees. That is my answer. That's the interior angle sum of the polygon. So if I add up all the angles, I end up adding up all these 180s. There's 4 of them, so 4 times 180. What you're going to discover on the worksheet that I'm going to show you in a little bit here is that there are 6 sides and we could only make 4 triangles. That's going to be a consistent pattern. There's always going to be 2 less triangles than the number of sides. So if you have 6 sides, you can make 4 triangles, so you did 4 times 180. If you have 10 sides, you could make 8 triangles. You do 8 times 180. And that's ultimately the pattern that I would hope you'd see in person if I were to do this in class. But I'm gonna guide you through that assignment, so I'm trying to give you a heads up on what you're about to see. All right. Oh, I don't know if I ever mentioned this in class, so I do want to mention it on here. I keep saying that the interior angle sum of a triangle is 180 degrees. Here's a really simple explanation for that. So um, why is the interior angle sum of a triangle 180 degrees? If I just draw a rectangle, I'll just make it a good looking rectangle. Here we go. If I draw a rectangle or a square, it really does not matter. Well, if it's a rectangle or a square, by definition, these are all 90-degree angles. So that's 90, 90, 90, and 90. So what do you have here? If you have all of these being 90 degrees, and you take this rectangle and you split it in half from one vertex to the other, diagonally, well, now you just made 2 triangles. Well, let's say you add up all the angles in this one and all the angles in this one. We know that they should add up to the total angle measure of the rectangle. So the original rectangle had 90 plus 90 plus 90 plus 90, or 360 degrees. We took 360 degrees in that rectangle, and we split it in half. We cut it in 2. So we divided it in half and we got out 180 degrees. So that's just a crude proof as to why each triangle has an interior angle sum of 180 degrees. All right, so as I said, I'm going to be walking you through, it says assignment number 1. I will walk you through this assignment. I am not going to be collecting this one. It's going to help you immensely, though, to get through the second assignment. So please walk through it with me. I'll guide you step by step, but please watch the video on this first assignment because the second assignment relies on the equation that we ultimately build in the first assignment. You'll have to actually use the equation that we build from the first assignment. All right, take care, have a good day, stay healthy, and watch that video. Thank you.